Given the head to a linked list, we need to return true if there is a cycle in the linked list, or return false if there isn't one. So what exactly is a cycle in a linked list? Well, a linked list consists of nodes and pointers to the next node in the list. And normally, the last pointer points to a null value to signal the end of the list. But if instead of pointing to null, the last pointer points back at some other node in the linked list, there is now a cycle. And if you try to traverse this linked list, you could keep traversing it forever and never reach the end. So now the question is, how can we detect a cycle in a linked list? To solve this, we'll be using an algorithm commonly known as the Tortoise and Hare algorithm. Here's how it works. We start by initializing two pointers, a slow pointer and a fast pointer. The slow pointer will traverse the linked list one node at a time, while the fast pointer will traverse the linked list two nodes at a time. Then, if the two pointers end up on the same node at some point, then that means that a cycle exists. So why does this work? Well, think of two people running on a track with no cycles. If we let them run, the faster one will eventually reach the end, which for a linked list is the null value, and we would know that there are no cycles. But if we put them on a circular track that does have a cycle, then at some point, the faster person would catch up to the slower one, which means that they would be back at the same position again. And so this is what we're looking for, and it's how we know that a cycle exists. Now, you may be saying, this is an example of two things moving continuously, but linked lists are made up of discrete nodes. Isn't it possible that the faster pointer could pass the slower one by skipping over it, so that they never land on the same node? Well, let's take a closer look at a few different scenarios to figure this out. The first scenario here is that the fast pointer has made its way around and is now one node behind the slow one. Then at the next step, both pointers would land on the same node and we're done. The second scenario is that the fast pointer is two nodes behind the slow one. Then at the next step, the fast pointer would be one node behind the slow one, and now we're back to the first scenario, where both pointers meet on the next step. And it's the same idea no matter how far back you move the fast pointer. At each step, the distance gets reduced by one node until eventually both pointers land on the same node. Now let's look at the code and see how we can do this in Python. We'll be using this definition of a linked list here. Each list node has two attributes, val, which is the number you see inside each node, and next, which is a pointer to the next node in the linked list. We are given a pointer to the head of the linked list, which I'll represent with this green label here. So the first thing we'll do is create another pointer called fast, which I'll represent with this orange label. So head will be the slow pointer, and fast will be the fast pointer. Now we'll enter a loop that will move these pointers forward as long as both fast and fast.next are not null. In other words, we keep looping until we reach the end of the linked list. So now let's move the pointers up. First we'll set head equal to head.next, so we're moving it up one node. Then we'll set fast equal to fast.next.next. So to break this down, this would be moving it up to fast.next, and then we have to do another .next. So now we've moved it up two nodes. Then, after moving up both pointers, we check if they point to the same node. Right now they do not, so we'll loop again. Head gets moved up one node, and fast gets moved up two nodes. Then we check again. Now I need to emphasize here that even though both nodes have a value of 5, this condition is still false, because remember, when you compare two objects using the is operator, it checks if both objects are located in the same place in memory. In other words, we are checking to see if they are the exact same object. In this case, they are two different objects that happen to have the same value of 5. So this is still false, and we loop again. Head gets moved up one node, and fast is moved up two nodes. And for the last iteration, head gets moved up one more, and now fast has caught up to head. Now when we check this condition, head and fast both point to the exact same object in memory, so we return true, and we are done. Now, if this had been a linked list without a cycle, at some point, fast would have reached the end of the linked list, and either fast or fast.next would have been null. So we would have broken out of this loop and just returned false, which means that there was no cycle.